Hello, BC Calculus students. This is Mr. Johnson, and we're going to start section 8.5, which is on power series. So as a quick opener, we're going to look at what is a series and review that terminology. So a series is a sum of terms, and our primary way of writing this would be the sigma notation, where we have, for example, n equals 0 to infinity, let's say, of some series a sub n. A power function is what we're going to obviously talk about in this section. That's the title of it. And we have already dealt with some specific power functions, but in a general sense, a power function is y equals x to the power of n. So basically, we have this polynomial of a number of different degrees. So for example, if you have a quadratic equation, x squared plus or minus other terms, that's going to be a power function. N, in this case, is any real constant. All right, and then we have an exponential function, just to make sure we know the difference here. An exponential function would be in the form of y equals b to the x. And so in this case, b is going to be greater than 0. B is going to be a positive real number, except that b is not going to equal 1. And so the main difference here between a power function and an exponential function is that a power function has the variable as the base, and it has a constant as the power, and an exponential function has a constant as a base, and the variable is in the exponent. All right, a power series is highlighted below, and it is in the form of c sub n. Keep in mind that it doesn't need to be c sub n. It could be a sub n or b sub n. It's just a dummy variable, but what it represents is that there is a generator in terms of numbers and n's in front or around the general power series, which is x to the n. So that c sub n could be really simple, like the number 2, or it could be really complex, like 2 to the power of n plus 1 divided by n factorial, or something along those lines. So keep in mind that it may look much more complex than the simple definition. Okay, but a power series is this infinite sum, and you have your first term and your second term and your third term and so on, and you can see that there's a pattern with x to the 0 power, x to the first power, x to the second, and so on. So your c sub n's, as you can see below, are the coefficients of the series, and then look at x as the generator of every single term thereafter. And what we're looking for is what values of x causes the series to converge versus diverge. Now, a power series can converge for a certain number of x's. Could be just one value, it could be multiple values, or diverge for other ones. And that is going to be our primary goal, is to figure out which x's cause it to converge versus diverge. The sum of the power series is what it would converge to. Okay, let's talk about one that we've actually discussed before. If you think about the series x to the power of n, we talked about this in section 8.2 when we talked about geometric power series. This particular series I'm going to list out really quickly here. So the first term would be 1, and then we have x to the first, and then we have x to the second, and x to the third, and so on. And that pattern continues, and then we have x to the n, and then of course that pattern continues after that. Now if you think about it, this is a geometric series, and this particular geometric series has an r value of x. So in other words, every single term is being multiplied by x. That's your common ratio. And then it has a starting term of 1. So a is going to be 1. Now we know, based on geometric series, that if the absolute value of r is less than 1, then it's going to converge. So this particular one, since r is equal to x, means that when the absolute value of x is less than 1, it will converge. You could think of that as -1 is less than x is less than 1 if you'd like. But again, this is going to be the convergent values of this, kind of like the basic or the bare bones. You could think of it as almost the parent function back to your higher algebra language, where we talked about the basic functions that we're going to start with. This is sort of our beginning power series. It's kind of the most bare bones power series. Now the sum of this series, think back to geometric series. We have the sum equal to a divided by 1 minus r, and this would be then 1 divided by 1 minus x. So that's going to be the sum of this particular power series as long as the absolute value of x is less than 1. What this means, and we'll talk more about this and show some visuals of this to help it sort of sink in. But if you were to take this particular function and look at a graph of 1 over 1 minus x, that's one of those rational functions that has vertical asymptote where x is 1. Again, you can graph that on your own. I would say maybe use Desmos or something where you could plug that into your Desmos equation, y equals that. That is going to be equal to the infinite power series or the infinite polynomial. So if you were to take, again, for example, Desmos, or your calculator for that matter, but Desmos might be easier to use, and you were able to maybe, let's just say you typed in the first 10 terms or the first 11 terms or whatever you want to type in, you would see that these two are very, very similar. I'm going to change my equals to an approximate sign here. These two are very similar if x is between -1 and 1. So again, outside of that, they're going to be very different. These two graphs are going to be very, very different. So don't get too bogged down by that. But if you were to zero in on -1 to 1 and change your screen so that it shows from -1 to 1, if you were to list 10 or 11 terms, if you were to list 20 terms, they're going to be relatively close during that interval from -1 to 1. The more terms you list, the more accurate it is. The less terms you list, the more off that approximation is going to be. But that's an amazing idea, is that if we were able to list an infinite number of terms, these two, this infinite power series and this rational function are identical graphically between -1 and 1 for x. So more generally, we want to kind of expand the idea of power series, and we've hinted at this up to this point. Here is a general formation of a power series where we say that A, and again, we've talked about this, A is the center of the power series. So the power series, it might be said to be centered at A, it might be about A, it might be in terms of x minus A. That A is the center of the power series, so it's where we're focused on. And then from there, we're going to talk about the radius of convergence as well as the interval of convergence for a particular power series. Now, any particular power series that's written in this form, and again, it says it down here, notice that x minus a is to the power of 0 is equal to 1. And if we have x equal to a, so if x is equal to the center, then it's going to be perfectly matched or mapped up. And so it will be convergent at that value. Now, there may be other values beyond that of which it converges, but it will converge when x is equal to a, just because mathematically it must. Let's go on to the next page. Okay, let's try example 1 and get a little bit of a sense of what we're dealing with these power series. And what you'll find is that the language in which we're talking about this has changed slightly, but the mathematics behind it is very much similar to what we've done in the previous sections. So in this case, we're looking for all the values of x for which this particular power series is convergent, and we're going to use the ratio test to do this, which is one that we've done before, so this portion is not new at all. We're just going to, again, to kind of change the format for how we explain it. So the ratio test says that we take the limit as n goes to infinity of the absolute value of n plus 1 factorial times x to the power of n plus 1 divided by n factorial times x to the n. And this should be less than 1 if it's going to be convergent. Now, from here on out, I'm going to condense how I write the ratio test to save ourselves time because it can be quite time consuming. So the next step, which is going to be in the future my first step, is that I'm going to write this by simplifying it down so I'm able to cancel really quickly. So in other words, I'm going to begin essentially with this step in the future where I'm able to cancel some terms here. Okay, so we have, let's see, x to the n is going to cancel, n factorial will cancel. I'll go ahead and write this one last time so you can see the simplified version. So we have the absolute value of the quantity n plus 1, and then that's going to be multiplied by x, and it's less than 1. So the question is, what x values cause this to be less than 1? The only x value for which this will be less than 1 because n is going to infinity is when x is 0. So for what so the question says, for what values of x is the series convergent? The only value of x at which it will be convergent would be 0. Now let's think about what this means regarding the center of convergence, which again we've discussed in prior sections. Let's talk about it now based on the previous page where we talked about x minus a. So if this particular series is written or thought of in the general form c sub n times x minus a to the power of n, that means that c sub n is n factorial, and x minus a to the n means that a is going to be equal to 0, which means that we have a center of 0. So remember, in this case, if we have x equal to a, or x is equal to the center, we know it's going to be convergent at a minimum. In this case, that is the only value for which it converges, because if x is anything else, then the limit of this will be much larger than 1, because n is going to infinity. Okay, let's take a look at example 2, something a little bit different. So in this case, let's just kind of brainstorm for a second. We have c sub n, which is equal to 1 over n, and the center a is 3 in this example. So again, if we're thinking back to the general form for a power series, c sub n is 1 over n. That's going to be the generator, that coefficient generator, and then a is going to be equal to 3. And let's go ahead and perform the ratio test and see if we can figure out for what values make this particular one converge. So we have the limit as n goes to infinity of the absolute value. I'm going to make this a little bit faster this time. So we have x minus 3 to the n times x minus 3 divided by n plus 1 multiplied by n divided by x minus 3 to the power of n. So I'm simplifying, or I should say just kind of rewriting the ratio test by essentially jumping into that second step versus setting up the whole very first step with a sub n plus 1 divided by a sub n. And we can cancel some terms here. So we have x minus 3 to the n canceled. N divided by n plus 1 will cancel as n goes to infinity. And our limit is done, and we're left with the absolute value of x minus 3 is less than 1. And again, if you think back to what we were studying in our last couple sections, we know that this is the radius of convergence, which I'll talk about at the bottom of this page. We know that this is going to be the center of convergence. Okay, and what we're trying to identify is the interval of convergence. So we know that the radius is 1, we know the center is 3. We can then break this apart and say that negative 1 is less than x minus 3, which is less than 1. And if we add 3 to both sides of that interval, we have 2 is less than x is less than 4. Now we come across a little bit of a challenge here, because with the ratio test, when we're studying the interval of convergence, the interval is okay, but the endpoints of the interval are indeterminate at this point. We don't know based on the ratio test what is happening at 2 or at 4 because the ratio test fails. Remember, if the ratio test provides a value of 1, then we don't know what it is going to do with regard to convergence or divergence. So therefore, if the ratio test yields 1, which it would at 2 and at 4 in this particular example, then we're going to be unable to know what happens, which means we need to test 2 and we need to test 4 separately. So we need to test the endpoints. We showed a little bit of this in the last couple sections, but now when we're talking about full power series, we're going to have to perform the entire interval test. So we're going to test x is equal to 2. And what I'm going to do is take x is 2 and I'm going to substitute it in for our equation up here for our power series. So I have the series from 1 to infinity of, if x is 2, I have the quantity negative 1 to the n over n. I know this is convergent by the alternating series test, which means that 2 is actually going to be included in my interval of convergence. But before I make a final statement, let's go ahead and also test x is equal to 4. So again, if I go back up to the original power series and I substitute 4 in for x, I get 1 to the n, which of course is just 1. I know this is divergent by the p-series test. We also know this is divergent because it's harmonic. So either way is totally fine if you want to state that. And what we now know is that the final interval of convergence will be 2 is less than or equal to x, which is less than 4, because at 2 it's convergent by the alternating series test, and at 4 it's divergent by the p-series test. So that would be the full interval of convergence. All right, at the bottom of the page, everything I was just trying to outline for you is put in place by definition. So if we have the particular power series written, there are 3 possibilities. The series converges only at the center. Number 2, the series converges for all x. So no matter what x is, the interval would be infinite. And we'll look at a number of power series where this is the case. The third option is the most common, and that's where you have some sort of value r, which we call the radius, and the interval is going to be convergent from the center out to the edge of the radius on either side of the center. If you're beyond the radius, then it will diverge. So as a quick little visual, if it's going to be helpful for you, if you have, for example, the center at A, and you have the radius, let's say that the radius will bring you this amount of space on either side of the center. That means that, let's say you have a value here. Whoops, let me change that. So let's say you have a value right here and right here in which you are ending the radius. So this is going to be a plus r, and not x plus r, a plus r, and this will be a minus r, and the value of r again is your radius, which is this length right here. And so the interval, if x minus a, the absolute value of that is less than r, would be all of the green right there, which would be convergent. Now again, the endpoints may or may not converge, and that's what we would test ultimately after we have performed the ratio test. But this is just a quick visual of what the 3 different possibilities are showing. And the third possibility is this restriction of this limited interval of convergence beyond just the center or any value of x. Now in case 1, so if we're looking at it only converges at the center, then r is 0, which means that we cannot move from the center at all. It's only convergent at the center. In case number 2, if it's convergent for all x, then r is infinite. So the radius of convergence is infinite. And then in case 3, again, that's the most common. Then we have our definitions of what I just drew here, which is the distance from the center to the outside of the interval, which is the length of r, and then on the other side of the center in the other direction with the length of r. Again, most of the tests you use to figure out the endpoints of the interval are going to be p-series and alternating series tests. I've seen plenty of comparison tests and limit comparison tests as well. It's very rare that you would have an endpoint and you would have to use like the collapsing sum test just because it's much more cumbersome. Usually it's a fast test, and it's mostly by observation that you're going to look at that type of analysis for the endpoint of an interval after the ratio test. Okay, this is the end of this first video. On the next video, we'll do some more examples. Thank you.